During this module, we'll conduct a virtual statistics tutorial applied to dimensional measurements of real manufactured parts. We'll take a look at data from a pump shaft and a conveyor bracket using data collected from real handheld instruments, including vernier calipers and an outside micrometer. By the end of this module, you'll be able to apply practical statistical analysis methods to real-world manufacturing measurement GD&T data, to create histograms, use probability density functions and statistics to answer questions about measured variables, and quantify precision intervals and confidence intervals, and identify outliers. The first part we'll measure and analyze is a pump shaft. The pump shaft is a core part of a centrifugal pump used to transport fluids in a variety of processes. The shaft has a number of important geometric features for holding bearings and seals, and for coupling to an impeller and a motor with a keyway. We'll use vernier calipers and micrometers to measure dimensions L1, L2, and L3 in diameters B, C, D, E, and F. We'll also measure and analyze a custom manufactured conveyor bracket cover. This aluminum plate with numerous holes and slots is used for mounting a conveyor belt motor and its sensors. We'll measure dimensions L1, L2, L3, L4, L5, and L6 along with diameters A, B, and C. For this tutorial, we'll be using data collected by students in a college engineering lab. Each student was given a part and a measurement tool to measure and record relevant dimensional metrology data by hand. In this tutorial, we'll be using that data rather than taking the measurements ourselves. Geometric dimensioning and tolerancing, or GD&T, is a system for defining and communicating engineering dimensions and tolerances. CAD models and engineering drawings like the pump shaft drawing shown here describe the physical object's nominal geometry and the permissible variation. We see side, top, and end views of the shaft with appropriately labeled dimensions and specifications. We can use this drawing for qualification testing to determine if the part was manufactured correctly. Note that the drawing specifies units, millimeters in this case, and a default tolerance, plus or minus 0.1 millimeter. Annotations on the drawing also specify non-standard or asymmetric tolerances like the keyway tolerance shown here, whose width can be up to 0.2 millimeters greater than the 4 millimeter spec, but the width cannot be less than 4 millimeters since the minus tolerance is 0. Here we see a similar conveyor bracket engineering drawing. The nominal tolerance of this part is plus or minus 0.05 millimeters and plus or minus 0.5 degrees. Here we see a vernier caliper used for precision measurements. The caliper has a movable jaw and a vernier scale in millimeters and inches. As the jaw opens and closes, it touches the part, and depending on the measurement, we use outside, inside, or step faces. The caliper includes a depth measuring bar, a thumb grip, and a clamping screw. Here we see an image from a vernier caliper measurement. Reading vernier calipers is a matter of practice and requires being familiar with the instrument and the principle of the vernier scale. With the principle of the vernier scale, and in this case because the vernier scale has 25 divisions, it divides the 0.025 inch main scale divisions into 25 additional divisions. So this results in the least count measurement of 0.001 inches, a thousandth of an inch. There's a step-by-step procedure for reading the vernier scale that's shown here, and it requires some practice and experience to make sure the measurements are taken correctly. A digital caliper is similar to the vernier caliper, except of course, as the name implies, it has a digital LCD readout of the measurement. Conveniently, the digital scale also includes buttons for zeroing, changing units, and powering the instrument on and off because it requires a battery. The resolution of the instrument in this case is the least significant digital digit, or 0.01 millimeters here. Pictured here we see the conventional and digital outside micrometers used for many of our shaft diameter measurements. The micrometer has an anvil and a spindle in which the parts are measured in between. A thimble is used to move the spindle in and out by rotation. The graded measurement scale is displayed on the outer sleeve barrel and on the thimble. A ratcheting clutch stop on the thimble ensures the micrometer is not over-tightened around the part. The conventional micrometer resolution here is a thousandth of an inch, similar to our vernier caliper. While this high quality and much more expensive digital micrometer can read measurements down to 0.00005 inches. This might be used for critical parts with very tight tolerances. Here we see a typical micrometer measurement and a step-by-step procedure for reading the micrometer. First, we record the reading corresponding to the first large number division on the sleeve that's at the left side of the thimble edge. That number is 2 in this case, and the value corresponding to that is 0.200 inches. Next, on the sleeve, we count how many small vertical lines are between the large number division identified before and the edge of the thimble. In this case, that's 1. We multiply that number of lines by 0.025 inch. So 1 times 0.025 inch is 0.025. And then on the thimble, we identify the 0.001 inch graduation that coincides exactly with the central horizontal line of the sleeve, or just below that line, recording the corresponding reading. So the thimble graduation here is 10, and the measurement is 10 times the resolution 0.001 or 0.01 inch. We don't have a vernier scale in this case, but from those previous measurements, we add them all up and we get the final reading 0.235 inch for this micrometer. Measurement task instructions for students working through the hands-on version of this tutorial in lab are shown here for reference. Tasks include tabulating measurements for the shaft and bracket and comparing them to tolerance limits for the purpose of quality assurance. Documenting results also includes recording make, model, and serial number of measurement instruments and specifications, as well as recording environmental conditions such as temperature and pressure. While completing the measurements in person, students record data in a shared spreadsheet by submitting data through an online form. Here we have a look at the form used to collect data. It includes email, name, section, instrument, measurement component, part serial number, the measured numerical value, and importantly, the measurement units. This is also tied to a spreadsheet. Here's a sample of shaft and bracket measurement data. Our tutorial will use this data for statistical analysis to answer manufacturing-related questions. It's important to note that our data represents many different measurement techniques with several different instruments, with many different people with different levels of skill and experience. Some of these measurements, like inside and outside measurements with a vernier caliper, are simple, while others are less common, like a depth measurement, or even less common, like the step face measurement shown at the top, middle, and L2. Common sense tells us that we shouldn't expect every measurement of every part from every user to be exactly the same. We wouldn't even be surprised if the same person with the same instrument recorded 3 different values for repetitions of the same measurement. It's one thing for the manufacturing process to have variation, it's another for the measurement process. As we think about statistical analysis and variation expected in these measurements, categorization of errors helps us identify and control assignable variation. We might even expect data entry errors in this case because we're using this form. We generally have 3 different categories of measurement error sources: calibration, data acquisition, and data reduction. Some of the specifics are listed here. One example that's common to consider is environmental, spatial, and temporal variation, which is part of the data acquisition process. Our statistical analysis includes several steps. For all of the measurement data, we'll compute the following statistics: count, mean, population variance, population standard deviation, maximum, minimum, range, median, and mode. And we'll assume that the data from each section includes the population. Then we'll create histogram charts for each pump shaft diameter. We'll compute the ideal number of intervals for the histogram using the Bendent rule, and we'll comment on the distribution shapes, looking at is the distribution shaped normally or skewed, is there bias or uniform distribution evident, is there high or low variance, are there outliers evident. And then we'll look at the conveyor bracket data, and we'll try to determine the range of values containing 70% of the population of measurements. We'll use the population mean and standard deviation and use the one-sided normal error function to compute Z1 and get a probability. For the pump shaft measurement L1, we'll also find the probability that the length exceeds a design value of 35.0 millimeters during any measurement. Again, we'll use the population mean and standard deviation and a Z-score using the normal error function. If we know that the true mean of L2 from the shaft is 50 millimeters, we'll find that what the probability is that the results are due to random chance alone. We'll also look at the L2 population mean and standard deviation, and we'll find the probability that a measurement is above 52 millimeters or that a measurement is between 51.95 and 52.05 millimeters, a tolerance range. Next, we'll randomly sample 10 measurements from pump shaft length L2 from one section's data. If more measurements were taken, we'll estimate the expected range for 95% of the measurements. We'll assume a t-distribution, look up the student's t for table 4.4, and we'll define the precision interval range. Then we'll determine the 95% confidence interval for the pump shaft length L2 using that sample with the standard deviation of the means, or the standard error. Then we'll use Chevanot's criteria to identify possible outliers in pump shaft L2 measurements for one section. We'll then ask ourselves how to estimate the number of measurements required to reduce pump shaft L2 confidence interval down to a small value, 0.01 millimeters plus or minus. We'll use an iterative guess and check method for that. And then for the conveyor bracket measurements L3, we'll compute the pooled mean, pooled variance, pooled standard deviation, pooled standard error, and mean square value using data from several sections based on the currently available data when completing this assignment. We'll also compute F statistics to test the equality of the population of means under the null hypothesis, and we'll compute a t statistic to compare equivalence of the means between one section data and the other sections. This concludes the introduction of the dimensional part measurement tutorial. We've introduced the parts, instruments, measurement techniques, data, error sources, and we've listed our statistical analysis tasks. We'll continue the tutorial with the actual statistical analysis in a subsequent video.